All right, welcome everyone. Today, we're extremely happy to have Ehud Altman joining us from Berkeley. Ehud is an expert in many topics. He's had a lot of recent work, interesting work on operator growth, chaos, and thermalization in many-body quantum systems, and also in measurement-induced physics. And I think that's what he's going to be telling us about today. So welcome, Ehud.
Thank you, Luca, for inviting me to Kadanoff Center's seminar. I gave Kadanoff seminar a few years ago, and it was great to visit, and hopefully I'll get to visit again in person. But I guess the next best thing is to do it on Zoom. At least the flight is not so exhausting, and the weather is maybe better. But so today I'll talk about physics of quantum circuits, and I'll talk partly about two papers that were already published with two fantastic co-workers in Berkeley. Yimu Bao is a graduate student, and Soonwon Choi, he's a postdoc. Next year he'll start as an assistant professor in MIT. And in addition to these two published papers, I'll talk about new work that's not published yet, and hopefully it'll be published in a few weeks, at least on the archive. Okay, so by way of introduction, you probably all know and heard about the huge progress in building and controlling quantum circuits. For example, one manifestation of that has been Google's quantum supremacy demonstration using a circuit of quantum superconducting qubits. This is a picture of their Sycamore processor and how it looks as a circuit. There are other platforms that seem promising, like trapped atoms, Rydberg atoms with tweezers, and ultra-cold atoms have all shown very promising results. And besides the promise of quantum computing, these systems also present new paradigms for many-body physics. For example, one can expect new emergent phenomena to arise from this new interplay of quantum entanglement, unitary gates, and quantum measurements, which is new and not something we're used to in usual many-body systems. So it's a new category of many-body system, and it's interesting to understand whether what are these universal new universal effects. There is just 1 second. Okay, so and then there are ways to look at it or demonstrate how it can be of fundamental interest is this question of how many measurements it takes to make a quantum state collapse. So we all know about this Schrödinger cat cartoon, where a entangled quantum state of a cat, which is both dead and alive, but everyone knows that this kind of state is very, very fragile. And the reason that it's so fragile is if you make one tiny measurement of one cell or one part of a cell of the cat, then it already collapses the entire cat. But is it true that all entangled states are so fragile that making just very few measurements will make them completely collapse and become essentially classical? And the answer is no, because, well, if we have generic entangled states, not like the cat state, there are a superposition of huge number of classical states, and the information is encoded in the non-local coefficients C1 to C2 to the n, and generically 2 to the n coefficients. And if you make just local measurements, you gain very, very little information about this quantum state, and therefore you don't truly collapse it completely. So now it makes sense to ask, how many measurements do you need to make in order to actually collapse the state in some, and is there a meaningful way to address systematically this kind of question? This will be part of what I'll talk about today. So as by way of background, this basically, this question was addressed systematically, or began to be addressed in the context of quantum circuits. And the way to phrase this question as something that can be studied by physics is you think of a circuit that entangles the state by applying unitary gates to the qubit. So you think of an array of many qubits. It could be one-dimensional or two-dimensional, but I'll mainly think of one-dimensional arrays for simplicity. And it's being advanced in time by operating more and more two-qubit gates. And it becomes more and more entangled. But on the other hand, during this process of entanglement, you also apply local measurements to measure the qubits. And as you know, when you have a projective measurement, what happens is that it projects you onto either the up state or down state of the qubit with some probability determined by these Baum probabilities, usual quantum mechanics postulate, and disentangles that qubit. So there is some competition between the disentangling by the measurements and the entangling and scrambling being done by the unitaries. And recently, or maybe 2-3 years ago, numerical results have shown that there is phase transition between a state which, if you have no measurements or very few measurements or very low frequency of measurements, you get volume law entangled state. Let me advance it, and to a transition from a volume law to area law. So let me make this a little bit more precise. What we're looking at is the evolution of a wave function under unitaries and measurements. Every time you make a measurement, you collapse the state into a branch in this tree. Every branch in this tree here basically corresponds to a series of measurements, vector m, m1 to m, last measurement. And the state evolves on this. If you start from an initial pure state, at every point, the state is still pure. And what we're going to be interested in when we say that there is a transition from volume law to area law entanglement, we're interested in this entanglement, which is an entanglement of this pure state, which is then averaged over the possible measurement outcomes, basically averaged over this ensemble of possible pure states you can get. Okay, this is very different from Lindblad type evolution, which first averages the state and gives you a density matrix. And in this case, we don't expect any transition. So this transition in quantum information, if you want, is a transition in the distribution of or the makeup of the unraveling of this open quantum evolution of the different trajectories associated with the pure states. That's what mainly I'll think about in this talk. And then the result was that if your measurement density or measurement frequency is below some critical threshold, then similarly to just unitary evolution, the entanglement entropy of, say, half the system grows monotonically, linearly, essentially, up to and saturates on a volume law proportional to the subsystem size. This is the entanglement entropy of a subsystem. And above the threshold, you basically, after some finite time, you saturate to an area law order 1 or constant entropy that does not grow with the system size or half subsystem size. This is the phase transition that people observed. So this is one kind of essential piece of the background that I'm giving. In all of these calculations and the theory that I will discuss later, these unitary operators were considered to be completely random in the sense that they're uniformly distributed. Each unitary is uniformly distributed as on the Haar measure. So it's called Haar random unitaries. And so you can think of this entanglement entropy after averaging over these unitaries as the typical behavior of a circuit, of a random generic circuit like that, okay? Second important piece of background is that these phase transitions can be understood as different phases of quantum information flow in the circuit. And there are two interesting perspectives to that. One perspective is the system perspective. How much information remains in this? When you measure a system, a quantum system, and make it collapse, eventually it loses any quantum information that was encoded in it. And you can ask the question, how much information remains in the system in steady state despite making measurements? So naively you would say, if you're making measurements all the time, information escapes all the time to these measurements, and eventually all information about the initial state or some reference state goes away. But this does not happen in this case. And the reason for this is that because of the scrambling by the unitaries, the quantum information remains hidden, and some of that information can never be revealed by measurements. So in the thermodynamic limit, when the system is infinitely large, then even after infinite time, you will have residual information in the system, and that can be quantified by the entanglement entropy with some reference state that was initially maximally entangled with your state. And if that entanglement of the entire system with the reference stays finite, or volume law, meaning it scales like the volume of the system, then there is you can say that there is a finite quantum channel capacity to this system. So yeah, this is the phase transition between a situation where there is a finite entropy to zero entropy in this case. You can think about this, you can forget about the reference and think about injecting, instead of pure state like we did before, we can inject a mixed state and ask whether this mixed state will be purified or not by the evolution. If we make many measurements, eventually each branch in the quantum evolution will be pure, or nearly pure. At least will not have an entropy, volume law entropy. And yeah. Sure. Question?
Can we expect to carry over to sort of a local Hamiltonian? So first of all, these are local unitary gates, and they're each independently sampled from unitaries. Is that right?
Yeah, that's right. They're local unitary gates. You ask a very good question. I believe, and we think, that all of this carries to Hamiltonian dynamics. However, it's, as you'll see, it is going to be much harder to address theoretically the question of Hamiltonian dynamics. The fact that we can average over the unitaries gives us a lot of theoretical power that we don't have with Hamiltonian systems. But I think it's a very interesting challenge to see what happens, and whether, even if it's there is something in Hamiltonian dynamics, maybe it's different universality. So all of this is very interesting, and I think this field is still, in its beginnings, and we don't know much. But as we'll see, I'm going to take the next steps to add more structure than just completely unitary, completely random unitaries. Okay. So there is a transition in the quantum channel capacity, and it's a purification transition. This was pointed out by us and by also a parallel paper by David Hughes and Michael Gallens. I want to also present a different perspective about the flow of quantum information in such a system, which I call the measurement perspective. Okay, so we can ask the question, so forgetting about the system, we're making measurements. How much information do we gain about the system from the measurements? Right? If the information is hidden, then because of this error correcting property, natural error correcting property by through scrambling, then we won't gain much information about the system. So we can ask the question, suppose I'm doing this as, experiment as in the lab. It means I'm collecting data. I'm repeating the experiment again and again with the same initial state. I'm collecting data, and my data are all the possible outcomes, strings of outcomes of the measurements. And then I collect this and make a distribution of measurement results, of the different measurement results. And one can ask whether if I do the experiment the next day, but some graduate student comes in and changes my initial state by a bit, by this unitary operator I have here, that acts on one side, say at the origin, at the initial state, will I be able to infer from looking at the distribution that these are that I started from two different initial states? And one can address this by now the measurement results correspond to a completely classical distribution, and there is object called the KL divergence that is a good measure of how different two classical distributions are. It's like relative entropy, and if that measurement is small, if that perturbation is small, then that is equal, the scale divergence is equal to something called the Fisher information times this epsilon squared. So the Fisher information turns out, and that is something we also pointed out in this paper, it turns out to be, there is a phase transition in this Fisher information. In the area law phase, above the threshold measurement rate, we basically gain as much information as we can about the system, just as if after infinite time, after infinite time in an infinite system, we'll gain all the information we can absolutely imagine we could gain, just like we measure, as if we measured every qubit in some computational basis initially. However, below this threshold rate, there will always be some missing information. And that's the phase transition from the measurement perspective. And you can see it from the and the nice thing about this is that there is no need for entanglement measurement. It's kind of more natural to measure if you want. It's still very hard, but at least it's somewhat more natural. And also, it requires only a classical record of measurement outcomes. Okay, so now the third piece of background that I want to I'll talk about in more detail later, so I just mention it here, that all of this can be addressed. One way to address all this systematically is to map this complex quantum dynamics to a more familiar problem of statistical mechanics. So as I'll show you in a minute, one can map these Haar random circuits to a problem of, at least in some sense, to something like an ferromagnetic Ising model. And the transition between the area law and volume law state is spontaneous, corresponds to spontaneously broken symmetry, and the entanglement entropy maps to the domain wall energy, where the domain wall is inserted between the subsystem A and B. And if you have a broken symmetry state, then you will have a linear domain wall energy, which would translate to linear with L entanglement entropy. So this is something you get out of this mapping, and it's kind of nice and gives at least some intuition as to what is happening in this dynamics. So there is a lot of progress in this. We understand some things. But there are many kind of interesting questions to ask. One of them, you already asked, what happens if you have more structure, like Hamiltonian dynamics? Another obvious question is, we have two phases, volume law and area law. That's it? Can there be more phases in such dynamics? What is the entire classification of the accessible phases, steady states of these circuits? How does physical symmetry of the circuit, for example, if we impose some structure like symmetries in the circuit, determine the classification of phases. Is it like ground state phases? Is it different? And also, what is the meaning of the different phases in terms of information flow and scrambling in the circuit? How do these different phases translate to signatures in measurement perspective, for example, and system perspective of the information retained in the circuit? These are questions I want to address mainly in this talk. But for this, I'll need to, okay, so first of all, let me give an overview, an outline of new things I want to talk about. So I want, as I mentioned, this mapping to statistical mechanics models was done for random unitaries. I want to discuss a slightly different mapping that will be useful to for considering states with more symmetry. And it's a mapping not to a statistical mechanics model in 2 dimensions, but actually a mapping to ground states of an effective Hamiltonian in the same dimension as your circuit. So 1 dimension in this case. So in this case, the classification of phases will be according to the symmetry of this effective Hamiltonian. The interesting, maybe somewhat surprising thing is that this Hamiltonian has a larger symmetry than the explicit symmetry of the circuit. So there are some kind of emergent symmetries that allow a larger classification, more phases than you would expect naively based on the circuit symmetries. So that's one thing. And I'll give 2 examples. One example is a case of a spin model, or not a spin model, circuit with Z2 symmetry. And I'll show that the phases are have an basically are characterized according to a larger D4 symmetry, and I'll show how different broken symmetry phases translate to information notions in the circuit. And last, I'll give the example of a Gaussian free fermion circuit, where it turns out that, I look at a circuit of Majorana fermions, so the only symmetry of the circuit is Z2 fermion parity, but we'll see that the phases of the circuit are actually, the possible phases of the circuit are classified according to an enlarged U1 symmetry. And that means that there is going to be, we show that there is going to be a measurement-induced Kosterlitz Thouless transition in this system, which was kind of surprising. People have seen some numerical evidence of something like that happening, but now I can give a theoretical explanation for it. So in order to get there, I need to give a little bit more background on mapping of this quantum information dynamics to equilibrium statistical mechanics. And this the first thing it relies on is a replica trick. So remember, what we want to calculate is the von Neumann entropy averaged over, so this is a von Neumann entropy, this is the von Neumann entropy for a particular branch of the particular trajectory of measurement results. This is the von Neumann entropy. You need to average over measurement results, and then you need to average over unitary gates, over all possible unitary circuits. So this is, of course, hard, both because of the averaging and because of the averaging over disorder, and because of the entropy, which is highly nonlinear in the density matrix, and there is no nice way to calculate it. So we solved two of these problems together by defining a hierarchy of replica objects, higher and Rayleigh-like entropies. They're not exactly Rayleigh entropies of this circuit, which are defined in this way. The details are not super important. It is important to understand that each one of these Rayleigh entropies is not really physical in its own right, because it averages a Rayleigh entropy of a particular trajectory, but it averages it with weight proportional to the probability of measurement of that particular measurement result to the power n. Okay, and the reason is, well, I'll not get to the reason, but in the end, the true physical meaning, I would say, is in the replica limit n to 1, where it exactly goes to the object that we are interested in, the von Neumann entropy with the correct averaging. So the nice thing about this is that now we have average of a problem where there is no logs. All the averaging is in the log, and we can represent it as a tensor network. Okay, and the reason we can represent as a tensor network is what you see here, this trace of rho to the n, basically means that you have, for the case n equals 2, which is the simplest, you will have 2 copies of your system. And because you're looking at dynamics, you have a forward and backward evolution. If you want to, you're looking at the 2 copies of a density matrix, so you have a circuit that propagates the ket, one that propagates the bra, and then the same thing for the second copy. So this is copy 1 star, copy 2, and copy 2 star. Okay, and in the end, you want to first trace over the B circuit, and this tracing is done by identifying and summing the outputs of the circuit in the B sublattice, and then you want to take a product of this density matrix, which is done by, identifying these objects, these parts, copy 1 identified with the bra of copy 1 identified with ket of copy 2, and then you want to trace, which is done by this. Okay, so in the end, you get the trace of rho squared, and in this construction, you can also convince yourself that the right power of the probability of measurement comes in as well, and that maps to a tensor network that now you need to contract in order to get the result. Of course, contracting this tensor network is very hard. It's basically impossible to do, but it becomes much easier if you average over, now I haven't done this yet, average over the unitary. So each unitary here has 4 copies, and they're all the same. So one important thing here, these are copies of the system that are basically not real copies, they're replicated copies, so they have to be exactly the same. Not only are they the same unitaries, and the same measurements occurring in the same places, but the measurement results are also the same in all of them. That's why the probabilities are also replicate. They're also higher, right? They're p to the n, because you need it. That's why it's very hard to measure that if you had real 2 copies, because you need to post-select trajectories that have exactly the same measurement results in them. But in this theoretical calculation, this is what it is, right? So So you take these and average over the unitaries and measurements, and what you get from this averaging projects this large Hilbert space. You see, you have a large Hilbert space because you have 4 copies basically of your Hilbert space, and that gives you a very large Hilbert space, and there are 2 legs going out of every unitary, but this projects it onto a much smaller Hilbert space of spin halves, 2 spin halves on every unitary. So this averaging procedure projects the Hilbert space down to a lower Hilbert space, and now contracting the tensor network is basically summing all the summing over all the possible configurations of these spins with some Boltzmann weights that look like an Ising partition function. Actually, this is what you see here is just an intermediate step with 2 spins per site on a honeycomb lattice. You can integrate out 1 spin per site and get an Ising model with Z2 symmetry on the triangular lattice. And now you have 2, this is only for the n equals 2 case, and this can be generalized for all replicas. It becomes a more complicated StatMech model, which I'll not talk about for now because it's more complicated. But already in this Ising model, you see a nice thing. one thing that I didn't tell you that is important, these different tracing in the A and B subsystems basically translate to different boundary conditions in the A and B sublattice on these spins. So, for example, in this case, the spins have to be down at the top in the A sublattice and up in the B sublattice, which means that the domain wall must end there. Now, if the system is paramagnetic and the S2 entropy is essentially the domain wall free energy. Okay, it just maps to the domain wall free energy. So if it's a ferromagnet, this domain wall free energy is order L, and if it's not, it's then it's a constant. There is no domain wall energy, and this exactly gives you this phase transition.
Can I ask a naive question?
Sure, yeah.
So how does this differ from the calculation people did before in random tensor networks?
Yeah. Very good question. So one thing that makes this a little bit more tricky than the random tensor network is that the measurement results here are not independent random events, right? They have to be evaluated by the Baum probabilities that depend on the state that you came from. And that complicates, basically it also makes the constructing a replica, replicated version of this somewhat more complicated. It's closely related, but this issue of not independent measurement results, but depending on the value of the state, it turns out that it's probably a different universality class even. Because of this, but it's very different. So if we would change this, that instead of taking the measurement results to be just Baum probabilities, they would be forced to be either up or down in some just randomly, completely independent of what is the state. Then it would be it would go to the same universality as the random tensor network.
I see. That makes sense. Also, maybe just naively, I think another difference which you mentioned is that here you're interested in calculating the Rayleigh entropies for the final state rather than some given sort of stationary situation. There is real-time evolution here.
That's right. There is real-time evolution. It might be different in the type of observables that we want to look at in the end, as we'll see. So there are other differences, right? But technically, for this issue of replicas and constructing a stat-mech model, it's very similar, but it's not identical. And the complication of this measurement probability is the main technical complication. So to speak.
Question. Sorry. Yeah. So how does this change? So can you apply this to a Clifford case?
No.
Okay.
No, because Clifford is not Haar random. We don't. I'll tell you that. We're now looking at something like a Clifford evolution where we can do something like this, but you can't apply exactly the same procedure because that relies very much on the fact that the gates are Haar random, not Clifford. So basically that they're uniform distribution on U, say UN or something, right? So and we still don't know, for example, people do a lot of simulations with Clifford. We don't even know if it's actually in the same universality or not. And they're conflicting numerical results. It's hard to say because there are no good results on non-Clifford. It's just too hard to calculate. So maybe that's one. Yeah. I want to say a word about, we have this emergent Ising symmetries. So where does this Ising symmetry came for the n equals 2, and there are higher symmetries that I'll discuss when n is larger than 2, more replicas. So where did the symmetry come from? I want to show that it's very physical, and there is something that is even beyond this replica method that is real about this symmetry and symmetry breaking. So where does Ising symmetry come from? It's basically coming from permutation symmetry of these two copies. It's kind of replica symmetry. It's not exactly replica symmetry because it's symmetry to permuting only the kets and not the bras, for example. And you can independently permute the bras. So there is more than just permutation symmetry. There is a permutation symmetry times another permutation symmetry. So in this case, in the Ising case, basically the two elements, the two spins, correspond to the two elements of S2, basically the identity and the swap. These are the two spins. So spin, I don't remember how I defined it here. I guess spin down is swap, spin up is identity. And of course, you see that there must be a global swap symmetry, both in the Hamiltonian and in the state. You can't really break it because when I take two copies and they're a tensor product of copy 1 and copy 2, I can just switch them and nothing will happen, right? It will be exactly the same state. So there has to be this global swap symmetry. But what if you apply the swap symmetry to, say, half your system? Well, if your state is a product state, just as a way to gain intuition, what happens when it's a product state? Nothing, okay? If I apply it only to the A subsystem, nothing happens. But if there is entanglement, then when I swap only half the system, I get a different state where now my entanglement crosses from one copy to the other, okay? And if there is long-range entanglement, there are many, many crosses like that. And this is kind of a physical reason for this domain wall energy that is beyond, this replica framework. It's related to you see that it actually measures the entanglement in some sense. Now, I want to show how this transition in the distinguishability of two states is also manifested in this framework. I'll do it just briefly because I want to move on. But one can, I told you that you can, if you make a small perturbation in the initial state, you can now look at your two distributions of measurement results. These are the red measurements, and there are many, many measurement results. And you look at the distribution after applying the same circuit many, many times, and you look at these two distributions and look at the KL divergence. Now, the KL divergence is also an object that's hard to compute because it contains, it's very nonlinear logs, but you can have a Renyi version of this KL divergence, just like a Renyi version of these entropies, and use the replica method in order to calculate them. And the n to 1 limit of this Renyi versions of KL divergence gives you back this usual KL divergence. And what you get here is again a Renyi version of the Fisher information. And for n equals 2, for example, what this Fisher information turns out to be, which is, I find, very, very nice, it becomes exactly the, 1 minus the broken symmetry order parameter, sigma z. So your phase transition is basically paramagnetic to ferromagnetic as a function of measurement strength. Is just the inverted ferromagnetic transition of the magnetization. And what it means in terms, because this is information, you see exactly, right when you're paramagnetic, you basically saturate this sigma z is 0, and then your Fisher information is the maximal. You have maximal information you can ever expect to get in the thermodynamic limit, at least, on the initial state, while it goes below maximum, so that some information is hidden when the measurement strength is smaller. And so we have a measurement of the domain wall energy, and we have another way to measure the order parameter itself through this Fisher information. Okay, so now I want to remind you, our questions was, so all of this was sort of background, maybe was new for some of you, so I went slowly a bit on this, but hopefully I'll get to more. my questions are, what other phases can there be, and how they can be classified by symmetry, and then translated to information flow in the circuit. And to address these questions, we'll need to go beyond, not Haar, that's Haar random, beyond Haar random unitaries, and allow more structure, such as in particular imposing internal circuit symmetries. So now I want to introduce a different model of a random circuit that make that will allow a nice mapping like that. So the model is actually very simple. So let me go over it a little bit slowly. What it has three types of elements. First of all, it has a two-site unitary gates. It can be more sites, but in principle, 2 is the simplest. And these two-site gates, they're basically like Hamiltonian gates. It's e to the minus I delta t times some random 2-spin Hamiltonian, okay? This is a random 2-spin Hamiltonian where this Jij, and we'll be able to impose symmetries on this Hamiltonian later, but for now I'm not necessarily imposing symmetries. So this Jij is a random Gaussian, it's a Gaussian random variable with zero mean in this case. Zero mean will be important. Okay. Then there is another type. So instead of Haar random, it's like a random matrix, but small random matrix, each one of them, random matrix Hamiltonian, for time step delta t, which will make small. As you will see, this is a model which will allow us to go to some kind of continuous time. Second, there are measurements, and the measurements basically look like this. The measurements are some measurement probability, which we'll call delta t times gamma squared, because we are making the same. We have the same measurement result in the two copies. This is for the case of 2 copies. We can generalize this to any number of copies. So for 2 copies, what this measurement implies is you do we sum over all the possible measurement results, sigma, and we project the ket bra of the 2 copies on this measurement result. Okay, this is the operator acting in this network for the measurement. And then there is also all these operators are flanked by these single site gates, Z gates, basically a random rotation in the Z direction, which we'll see for simplicity, it's great to take it uniformly random from 0 to 2 pi, this angle of rotation in the Z direction. Okay, so it's completely random angle of rotation. The nice thing about this random angle of rotation is if you take this, if you average over this, so you see this gate, you average over this gate, you don't have to follow this. This is kind of details, but it's very easy. It's 2 lines to show, basically 3 lines to show that what you get is a projector on 6 states. So you start from 16 states and you project into 6 states. And these 6 states are, it's very nice to organize them into 2 quantum numbers, m going from -1, 0, and 1, and s, which is like a spin half variable, which could be plus or minus 1. And it turns out that in this dynamics, s is completely, s is conserved, so s is going to completely disappear, and the only, so this becomes like, after averaging, it becomes a network of operators acting between Hilbert space of 3 states on each side. So it's like a spin 1, okay? And we can, and moreover, we can write the transfer matrix that takes us from one row to the next. Because if we take delta t to be small, we can take it to be like an effective Hamiltonian, except for one thing, that this effective Hamiltonian runs in imaginary time. So it's like an imaginary time path integral with an effective Hamiltonian. And if we go to long times, what it does, it simply projects us onto some ground state of the effective Hamiltonian. So this dynamics, at least for the small delta t, and under some conditions, for example, that these Jijs are random and zero mean variables, Gaussian zero mean variables, this is what it does. So basically what you get is that what you insert here is doubled density matrix of the initial state. It propagates with the imaginary time evolution by an effective Hamiltonian, and then you measure something at the end, and the measurement at the end looks always like this. So for example, what we want to measure is the entanglement entropy. So that's one example. So the entanglement entropy we want to measure will be, well, let me measure e to the minus the entanglement entropy. E to the minus the entanglement entropy is basically taking the swap operator in subsystem A and sandwiching it between this ground state, which you generate by a long time evolution, and some reference state. So unlike in equilibrium, all the interesting measurements, or most of the interesting measurements we can access, are not expectation values in the ground state, but they're matrix elements between the ground state and some reference state that happens to be a simple product state. Okay, so this is this has analogies that, by the way, in classical statistical mechanics of non-equilibrium disease models and diffusion reaction equations, where the master equations actually map to such a quantum Hamiltonian. In this case, because it really comes from a quantum problem, we can have more structure, and the quantum Hamiltonian can give us various quantum states like topological states and so on that you cannot get in the classical case. But in some senses, it's similar, I think. Okay, so this is a new type of model with mapping to an effective Hamiltonian. Now, what is the symmetry classification? So suppose each circuit, the circuit itself has an internal symmetry G. So we have these n copies, and we can permute them. This gives you us one symmetry, which is Sn, but there is also an internal symmetry G. And we have the same symmetry for the left and the right, or if you want, ket and bra. So the total symmetry is G to the n, basically G cross G cross G cross G, semi-direct product with the permutation group Sn, times the same thing for the bra. And then there is a semi-direct product with another Z2 symmetry that I haven't talked about yet, which exchanges ket and bra and complex conjugates. This symmetry actually corresponds to, this is the symmetry that makes sure that the time evolution is Hermitian, that the density matrix remains Hermitian. Okay, so that corresponds to some dynamical symmetry that's also here. And probably has interesting consequences that I have to say we so far haven't investigated deeply, partly because it does not manifest in the n equals 2 replica. It only manifests at higher replicas.
Is it related to time reversal, to some sort of
It's related to some time reversal, but it's not exactly right. These are not time reversal invariant problems because we have measurement, right? So it actually behaves like time reversal because it's an anti-unitary symmetry. Mm-hmm. So it looks like time reversal in the effective Hamiltonian. The thing is that it becomes kind of trivial in the problems because you know in time reversal is something like U times complex conjugation. The problems we're looking at are real, and the complex conjugation doesn't do anything, and then U is trivial on this on the projected subspace for n equals 2. So basically, this symmetry is not manifest there. So I have some thoughts about what it does, but we can discuss this later. So anyways, let me give an example. And the example would be a circuit which has the simplest symmetry, just Z2 symmetry. So what is an example of a circuit that has Z2 symmetry? I allow these gates. So remember, one of the gates I need for this mapping is this local Z gate. That will always be there. So this is the local Z gate. I also have two side Z gates, I allow any side Z gate. So in principle, I can have 3 side Z gates and so on. The symmetry generator, by the way, is a product of Z on all sides. Okay, so now I allow only an even number of X operators, and that will have, so the unitary part will commute with the symmetry. And the measurements, if I measure only Z on site or or X and X, 2X is basically only X times X on 2 sides. So I don't measure X alone, but only X times X. That will also conserve the Z2 symmetry. In this case, we have a swap symmetry. We have parity symmetry for both the ket and the bra. For the 2 copies. We have parity for copy 1, parity for copy 2, and our total symmetry is D4, but the full dynamical symmetry, as I mentioned, is D4 cross D4 times Z2, this Z2 star. But it turns out that for this projected Hilbert space, this is reduced back to just D4. And you can represent this D4 as the symmetry of the square, where S2 is like a mirror of the across the diagonal, and the 2 Z2s correspond to mirrors on the horizontal and these 2 blue lines here, so midlines. Now, what are the possible phases in this case? The phases will be classified by the symmetry of this effective Hamiltonian, so it will be classified by D4, and we have many possible phases. I list some of them actually. So we can have a trivial phase, basically no symmetry breaking at all and nothing really interesting. That's basically the trivial area law phase we had before. We can have spontaneous breaking of Z2 symmetry without breaking of the S2 symmetry. With so S2 is still present, but some Z2 symmetry is broken. And this gives you a non-trivial area law phase. And this has been discussed, this kind of phase has been discussed by Tim Shih, for example. And they did the Clifford simulations showing this kind of phase and phase transitions between the broken symmetry and non-broken symmetry phase in measurement-only models. But you can have more. You can have spontaneous symmetry breaking of both the S2 and Z2 symmetries. And that gives you what we call a trivial volume law phase, which hides all information, as you expect from a volume law phase. But you can also have a spontaneous symmetry breaking of S2, which gives you a volume law phase, but it does not break the Z2 symmetry. And we'll see that this is kind of a non-trivial volume law phase. And in addition, you can have other phases like SPT phases that are protected by D4 symmetry. So naively, you would say, well, these Z2, if I have Z2 symmetry, I cannot have a SPT phase because you need at least Z2 cross Z2 for that. But because of these higher emergent symmetries, you can in principle have also SPT phases protected by D4 symmetry. And the question is now, what do they mean, all these phases? So to give some idea of this, wow, how much time do I have? Probably not much.
Still 10 minutes officially, but 10
minutes. Okay, good. So let me quickly go through this. So how do we detect this broken Z2 symmetry? I'm oversimplifying a bit because, as I said, there is D4 symmetry. So there is more than just a Z2 subgroup. There is a whole Z2 cross Z2 subgroup that does not involve S2. So one can ask where how the different Z2 symmetries are manifest here. But let me kind of put this under the rug a little bit and simplify. So one way to measure the symmetry is, or to see whether what's the consequences of having or not having this symmetry is to go to your output state and measure and apply the symmetry operator to your output state. So let me not apply the symmetry operator to the entire state, but let me apply it just to some string of sites in subsystem L. If the system is symmetric under this symmetry, this would not do anything really to the state, and you should get basically the same state back up to some very small perturbation, and I should get some constant. On the other hand, if I apply this and to this boundary, and there is a broken symmetry state, what this will do, it will insert the domain wall in this 2+1 dimensional one plus one dimensional quantum mechanical problem, which will cost domain wall energy, and I'll get this this will go to 0 exponentially. So in the symmetric phase, I expect this string to go to a constant. By the way, I'm measuring this. What do I mean when I say I'm measuring this? Every time I measure this parity, this is basically the parity in this Z2. I'm measuring the parity of, say, L sites. Every time I'll get a different result, 1 or -1. What I'll need to do is I'll need to measure the parity squared, and then average. And this parity squared measurement goes directly to a disorder parameter, if you want, the dual to the Ising order parameter in this statistical mechanics model, and you get that it has short range correlations, meaning it goes exponentially down if the system has symmetry, and it goes to a constant if it does not have the symmetry. And this is again related to a domain wall operator, inserting a boundary domain wall operator. So this is one way to and one can interpret this in terms of information that if you make some we're measuring parity. Z2 symmetry is associated with conservation of parity. We're measuring this parity. If we have a definite parity, this should go to 0, right? Because we have a well-defined definite parity. It's parity operator gives me always 0, and this should go to 0. Indeed, if I have a symmetric phase, this is I should have if I have a definite parity, I should always get either +1 or -1. When I square, I have always 1, so it should go to a constant if I have a symmetric phase. If I have a state that breaks parity, I have indefinite parity. So clearly, if I do that, I'll always get some average 0, and I'll not get any signal from this. So this is one way to understand it, to get it. Another way is to apply a perturbation at the origin, just like we applied before. Instead of applying a perturbation that makes the two copies different, what we now apply is a perturbation that breaks the symmetry at the origin. So this perturbation is a perturbation that breaks the Z2 symmetry a little bit, so introduces a little bit of parity indefiniteness. And now we look at the difference between the entropies of measurement outcomes in with and without the perturbation. And it turns out that this exactly maps, just like before done for the entanglement entropy. Now it maps to 1 minus the order parameter of this Z2 symmetry. So, and what it means is that basically there is one phase, even in the area law phase, there is one phase, which is the phase that the phase that does not break, has the symmetric phase, basically completely reveals your parity, whatever is so you introduced indefinite parity, and by doing the measurement results, you know that you have introduced an indefinite parity. It reveals this information about parity. While the other phase, the broken symmetry phase, hides this information about parity in your system. So it's a revealing and hiding phase, but now generally information is revealed, but information about parity is actually hidden in this area law phase. Okay, so now the last part of my talk, I'll go over it quickly, but I find it really, really cool, so I want to go over it, is free fermion circuits. So I can also do exactly the same for free fermion circuits, and we're looking at free fermion Majorana circuits. So the type of gates we can have instead of spins now are Gaussian gates like this, where Ji is like a coupling between two sites. It's like hopping gamma I minus 1, gamma I bar. It's like a Hamiltonian gate for Majorana hopping. We also have on-site parity measurements of Majoranas. So this is, each site has 2 Majoranas, and we're measuring the parity of a site. And we can also make a bond parity measurements between sites. And as before, we have a single site gate, which we average on. And that gives us, and from this we can generate an effective Hamiltonian just as before. I'm not going to give the details, but I want to talk about what previous results show us. So first of all, there was a nice paper by Xiangyu Cao and collaborators that showed that in free fermion systems, there is no volume law phase. There is only area law, maybe with log corrections. The reason for that is that because the gates are Gaussian, they're not scrambling enough. However, there was some numerical result, which we found pretty interesting and mysterious, showing that there is a whole phase with log L entanglement. So if you make only weak measurements or few measurements, you get not immediately area law entanglement, but log L entanglement. And then there is probably a transition from this log L entanglement to something else. This was seen numerically, and it was not clear that it's correct. And also it was seen in fermions with charge conservation, not Majorana fermions. So they thought that has to do with this U1 symmetry. I'll show you that this actually arises also for fermions without U1 symmetry as follows. So the way it goes is that these are, we need at least 2 copies. This is one Majorana chain, another Majorana chain. And now we can map it in a very similar way to an effective Hamiltonian that becomes a spin 1 model, just like before. This spin 1 model turns out to be just an XXZ model with single site anisotropy term, where the different terms here correspond to the hopping of Majoranas, the bond measurement strength or bond measurement frequency, the site measurement frequency, and so why do you get an XXZ model which has U1 symmetry from Majoranas that don't? And the reason is actually pretty simple, because you needed to look at 2 copies which are imposed, they have to be identical. So if you take 2 copies of Gaussian Majorana fermions, that gives you effective model of Dirac complex fermions, which you can create by taking Majoranas from the 2 copies, 1 plus I Majorana from the second copy, and you get a conserved charge, which is the sum of the charges of all these fermions, and that provided that they're quadratic and identical copies. So that gives us a U1 symmetry. Moreover, remember, this is only the ket. There is also a bra, which corresponds to the time reversed. So actually, there are 4 Majorana chains. And these 4 Majorana chains, you can think about them as long as you don't couple ket to bra, which you don't as long as you don't have measurements. Then you have you basically have 2 chains and the time reversed partners, which correspond to spin half fermions, and which give you SU2 symmetric model. So only without measurements you have SU2 symmetry, and with measurements you have U1 symmetry. So if I turn off all the measurements, this, and this, then actually I get a Heisenberg model with SU2 symmetry. But I'm going to look at measurements, and this XXZ model has been looked at, been a lot in the past. There are numerical simulations. We know exactly the phase diagram, and the phase diagram looks like this as a function of bond measurement strength and site measurement strength. Bond measurement strength, right? If you remember, it's measuring Majorana's parity off-site, and site measurement measures the parity on a site. So at exactly 0 measurement strength, you have SU2 symmetry, and that allows for a volume law phase, okay? Because you have a ferromagnet, although you have a one-dimensional model, a ferromagnetic model commutes with the order parameter, and of course you get long-range order, and it's broken symmetry volume law phase. But immediately when you turn off on measurements, as we saw, this is a singular perturbation. It immediately breaks the SU2 symmetry down to U1. So what you can get is only that you go from true long-range order to only power law order, and that's a whole critical phase that you get here. Oops. That's this critical phase you get here, and at some critical value of measurement, you get a transition to an area law phase. I'll show you that in a minute, and you can also go in the other direction where you increase the bond measurement strength, and that brings you into another area law phase, but in this case it's an SPT phase of the spin 1 model. It's the Haldane phase. So the question is whether we can distinguish between them, and there is also a trivial area law phase. So these free fermions actually have already two non-trivial phases in them, just because of this enlarged symmetry. I guess I'm more or less out of time. So first of all, I explain in this way, we explain this numerical result, why you have a whole phase with U1 criticality, basically where we have log L entanglement that goes as log L. We also, by the way, this topological state is very closely related to a phase that was discussed by Adam Nahum and Brian Skinner based on an only measurement model, where they only measure Majorana's either on-site or on bonds. And when the rate of one type of measurement becomes larger than the other, you transition between these two states. But what we point out is that this transition is at least closely related to the transition between the Haldane phase and trivial phase. Okay, so I maybe I'll skip this. One can look at signatures of these phases again by looking at the variance of the parity operator, and this maps to local operators in the bosonized picture of this XXZ model. And you can basically you expect that this parity string will go to power law in the critical phase. It'll be constant in the trivial phase, and it will go to 0 exponentially in the Haldane phase, which is what we see numerically. So I'll just flash the numerical results. This is, we numerically simulate both the parity string and the entanglement entropy, and for weak values of weak measurement or low measurement probability, it has a power law decay, and at some value of measurement, it basically sticks to become just a constant. So we haven't had a chance to analyze this phase transition in detail, and it's also probably not easy because it's a Kosterlitz-Thouless transition. It's at least expected to be Kosterlitz-Thouless transition, so you need to go to pretty long systems probably to really nail it down. But at least it looks very much like, and now we have actually results from all over this phase diagram. So we have results of going through this transition and this transition and this transition. And, at least in our limited system sizes so far, it looks like we can capture all three phases. And the phase transitions are harder to capture. Okay, and I'll just summarize. So I discussed the mapping from quantum information dynamics on quantum circuits with structure to ground states, structure like symmetry, to ground states of an effective Hamiltonian. the phases are classified according to a larger symmetry of the effective Hamiltonian that includes a combination of the intrinsic system symmetries and the permutation symmetries of the replicas, and the requirement of hermiticity of the density matrix. And I've shown two examples. One is a spin model with Z2 symmetry, and that goes to effective Hamiltonian with enlarged D4 symmetry, and discussed how it translates to the different possible phases. And I've shown you a Gaussian fermion circuit where the enlarged symmetry is even bigger. It's a U1 symmetry, and that gives rise to an induced KT transition, measurement-induced KT transition. And basically, the outlook is there are a lot of questions we need to understand. First of all, I only looked very closely at replica index 2, but in reality, we need to understand what happens in the replica limit to 1. So we need to look at all other replicas. And I think the way to go is to define properties which have a well-defined replica limit. For example, we've shown that the Fisher information associated with measurement results with respect to initial state is a property that actually has a well-defined limit in the replica limit. So at least phases that have a well-defined, that have a signature that is meaningful in the replica limit, I think should survive also the analysis of higher replicas. Also, we don't understand so well this hermiticity symmetry, and what's the what happens if it's spontaneously broken, for example. I have some interesting thoughts about that, which we can discuss privately. So far, it's this kind of time reversal-like symmetry, and what's its role in this classification of phases. Another question is that all of what I talked about here is very hard to measure experimentally because it requires post-selection of measurements. The question is whether quantum circuits have similar transitions, analogous transitions, maybe in systems with more structure, which can be identified more easily with true physical observables that are linear and not quadratic in the density matrix, for example. So that would be much easier to see in a circuit, and maybe even will have more implications to quantum computing and resilience to noise and errors, for example. So making connection between these transitions and actual resilience of a quantum state to noise is also another challenge. Thanks.
All right, thanks, Ehud, for the very nice talk. We can take a few questions.
I have a question about, so the system size, the larger system size, maybe it's a technical question. Yeah. So for this smaller set of gates, does it allow you to go to larger system size because you're not using the full hard unitaries?
Going to larger system sizes, you mean in numerics?
Yeah, in numerics.
I'm not sure. I mean, in any case, it's still, if you want to do exact numerics, not Clifford or Gaussian fermion circuits, which you can do large systems, then I think the numerics is still exponentially hard. Maybe at the margins, it helps you a bit, but I'm not sure how much. Frankly, we haven't tried to do any kind of exact numerics. We did what we did, which I didn't show because I didn't have time, basically we wanted to identify all the phases we had. We weren't sure they're actually allowed. So in order to see that they are allowed, we devised models that would give rise to those phases, basically phases that are volume law broken symmetry, volume law non-broken symmetry, and area law broken symmetry, non-broken symmetry. We have that models that do it, but we have them with Clifford circuits. And doing it with non-Clifford circuits, we could probably just go to very small system sizes. 20 something at most. But we didn't try. Yeah. It would be, nice to find an efficient way to maybe do it. Well, one way, okay, another way to do numerics, but it's not exact numerics, is to map to our quantum Hamiltonian and do numerics on our quantum Hamiltonian. But of course, that will be numerics only on the n equals 2 replica, right? Or when we can do maybe for n equals 3 and n equals 4, but then it begins to be too hard at some replica. And these are kind of tractable ground state problems that you can do with ground state DMRG. So that's a nice thing. And I think my understanding is that to capture the phase transition correctly, you need to basically look carefully at all replicas and do the replica limit. But if we want the specific phases, I think n equals 2 replica probably is good enough. Although there are some issues with that too. Maybe n equals 2 replica, but then introduce this disorder in a more in a better way. So maybe there is even better ways to do the n equals 2 replica that we need to learn. But for capturing the phase transitions, I think that would be that would be hard to do in numerics for any non-Clifford or Gaussian fermion problem.
I see. So the phases identified by looking at n equals to 2 replica will still be there if you look at higher replicas. But
okay, I think, but there will be more phases that probably will disappear or collapse to the same phase. So there are, I think it's important to look at any n equals 3 replica at least to capture all the phases. For example, we think that there is an interesting phase, so there could be an interesting phase associated with spontaneous breaking of this fake time reversal symmetry that does not manifest in replica n equals 2. And we think it's related to establishment of entanglement negativity, volume law entanglement negativity, because this time reversal like symmetry exchanges ket and bra. So if you take subsystem transpose like that, that basically corresponds to entanglement negativity. So I think that's very interesting, because what we're interested in now is to look at models that are much more like all the measurements we're considering here are like they're measurements that are registered and we know the measurement result. But in real circuits, for example, there are many unregistered measurements or just decoherent processes that you cannot keep track of and make your system basically bring you to a mixed state. But we believe, and then you cannot have this S2 is broken by this mixing. But this time reversal, fake time reversal symmetry is still there, and you can still break it. And maybe there is a transition in which your density matrix goes from area law to volume law negativity. So that's something we're pursuing now.
I see, because the negativity captures the quantum correlation. Right?
That's right. But as far as I understand, it's known, but we also kind of encountered it, that the entanglement negativity is trivial for n equals 2 replica. You have to go beyond n equals 2 to see it. And that is consistent again with that symmetry, time reversal symmetry is trivialized in this n equals 2 also. So so I think there is interesting things to understand there. And it's maybe even more relevant to actual circuits and how resilient they are to real decoherence.
Okay, thanks, Ehud.
Any other question? Right. If not,